Okay, given a function of two input variables, x and y, the gradient is a vector function. So here's something strange. What we've done so far is said you have this f of x comma y, and then the partial derivative with respect to x, also noted df over dx, and the partial derivative with respect to y, denoted df over dy. Those two things happen to be of the same kind of creature as f of x comma y in the first place. They happen to be functions of two input variables. But now what we're doing is saying, let's take those functions of two input variables and stick them into a vector. Make them the components of a vector, right? With angle brackets, comma. And so what we're going to get out of this is a vector function. And that vector function is called the gradient. So it's got this upside down delta, capital delta symbol. We could have, by the way, just to get you used to some other notations, right? We could have said that this was defined delta, not delta. This symbol is actually called nabla in LaTeX, but we'll say gradient. Right? So the gradient of f equals f sub x comma f sub y in angle brackets. Or if we wanted to not use the angle bracket notation, of course, we could have the ij notation as well. So there's actually going to be lots of different notations for the same thing. Recall that a vector function always outputs a vector. So let's do this, right? Let's find the gradient of f if the function we're talking about is f of x comma y equals x to the y power. So what we're going to need, right? So this is just copying from the formula above, right? So the gradient is, first component is partial derivative with respect to x. The next component is partial derivative with respect to y. And so what's the partial derivative with respect to x? Well, you look at x to the y. Remember, y is constant. So think about, like, how would you differentiate x to the 8th? That'd be 8x to the 7th, right? So you need to apply the power rule. If the exponent is a constant, and here we are treating y, even though y is technically a variable, we are treating it like it's a constant. And so that's why you see here y times x to the y minus 1. For the next component, we need f sub y. So we should look at x to the y, and how would we differentiate this if y is the variable and now x is a constant? And really, to simulate x being a constant, let's just pretend that x is 8. How would you differentiate 8 to the y power? That should use this exponential derivative rule, 8 to the y times ln of 8. So we will say x to the y times ln of x. Okay, so here it is. That's the gradient of f, right? It's basically just a listing of all of the partial derivatives in order, right? So partial with respect to x, partial with respect to y. So let's do this again. Find the gradient of the function xy sine of x plus x squared y to the 4th. And so same deal. We need to take a derivative with respect to x, and that's going to be the first component. It's kind of long here. Let's go through it, right? So we're going to need to apply the just for the first term, there's an x in what's a product, and it's a product that has the variable x in both parts. So we need to apply the product rule, right? So first times derivative of second. Okay, so that's why we have xy times and derivative of sine of x is cosine of x, plus the second part times the derivative of the first, right? So the second part is, let's say, sine of x. There it is copied, and the derivative of the first. Well, the derivative of xy should just be y, again, if y is constant and x is variable. And then x squared times y to the 4th. Well, y to the 4th is a constant. Let's just copy the constant and then differentiate x squared, and you get 2x. Okay, and then you can work through, maybe I said enough, but after the comma, you'll see the partial derivative of f with respect to y.